Hi, this is Professor Huang. Today I will do a quick review of the course I taught at the SysTech. This is SysTech, um, Swarm Intelligence, Swarm Robotics. That's our GitHub. If you are interested, you can go take a look there. We work on Swarm Intelligence. I taught this course mainly for postdoc fellows. As well for PhD, master. A few bachelor do attended my seminar, and some of them they study in USA. Some are in Europe, and some are, of course, in China. So I taught this course for one semester, 2018, that's a dog year, and all the way to the 2019, that's pig year. And these are my membership: American Math, Chinese Chemistry, Canadian Physics. The topic I was talking is functional analysis. So the functional analysis is a very, very important course for whoever want to do PhD in science or engineering. So if you are in literature or culture, you don't need that. But as long as you are in science or in engineering, you will need that. Why? Because this is a very, very fundamental mathematics. Mathematics is about infinity stuff. So that's the snake. The snake, when it, she's hungry, she eat her tail. That's the where the sign of infinity comes from. Infinity means snake eat tail. So all the mathematics is doing nothing but the snake eat tail, infinity stuff. And I'll go over four parts. First is this infinity, and then I talk about the space, and then I talk about the operator, and then talk about the spectrum. So the spectrum is kind of we use when we're doing brain wave analysis, like FFT is a spectrum. And the operator is related to these C++, because the guy who invented C++, he doing nothing but study this functional stuff. That's where the C++ is so complicated, because the it was invented by a mathematician who studied uh, this course or teach this course, functional analysis. That's why I said if you work in engineer, you got to know that. So the definition, I grabbed a lot of stuff from Wikipedia. So functional analysis is a branch of mathematics, the core which is formed by the study of vector space, some kind of limited related structure. For example, inner product. So inner product is very important. Um, like a correlation is inner product. Convolution is kind of inner product. And the norm is a distance. Like when we do algorithm for Amazon recommendation, we either go with the inner product or we go with the distance. Norm is basically distance. Or topology. Topology is kind of logic between algebra and the geometry. And then the linear functions defined on this space and the suitable respect these structures. It sounds very easy theory because it's a linear algebra vector space, but it can be very complicated. Why? because these vectors can be infinity dimension, like A, B, C, D, E, F, G, dot, blah, 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 until snake too hungry eat her own tail, until infinity. So you expect that you play with the vector that has infinity long. The history roots um, from study of space functions relate to like a Fourier transfer. FFT is Fourier transfer, and continuous unitary operators. So these are because it's a continuous, like I was talking about integration or differentiation. Those are in the continuous domain. Summation is discrete. And then if you do 1.5 integration, that's kind of complicated. Or you do infinity dimension, whatever. So they relate to differential and the integration equations. So that's why function analysis is huge. It covers all the mathematical branches almost. And these are the founders. It's not the founders company. It's the founders of functional analysis, the course, the guy who invented the word called a functional analysis. And then that's um these are our ancestor, Helbert David and Hadamard. So these two are the guy who invented. And then after that, many people do a lot of applications like Arena, Volterra. Did a lots of engineer. Anything nonlinear, you need a Volterra to deal with it. And our semi theory really coming down from like a Paul Levy and then Mandelbrot, which I already explained before, Mandelbrot. So we coming from there. And these are the books, very old, 2010, 2005, 4, uh, because the theory is old. This is when the people figure out the theory. It's a long time ago. It's a long time ago. It's Hilbert is fighting with Albert Einstein. So it's Albert Einstein time. And today's Chinese expert are two professors. They both are Professor Yao. The first Professor Yao is in mathematics. He got the Fields Medal award by U of T. That's the Nobel Prize in mathematics. So Professor Yao get that medal. And like we used to work on these MPPK, and then Professor Yao's students actually break our algorithm. We fix it. We all ask Professor Yao's student to go break it again. And the second Professor Yao is not the mathematician. Um, he's a computer science. So he got the Turing Award. So these are the two uh, Chinese experts in mathematics and computer science. Um, when we this this slice is very long, it's 95 pages, so I will go really quick. One example is a complex algebra, because I keep telling Nada go study complex stuff. So the algebra you learn during your master or bachelor are real, not the complex. And that these are up level. So if we want our AI works harder or be better than Manus that the Chinese company and bought by Meta, we need to get into this area, complex. And these are the code our team worked out. I posted there. Then not necessary. I wrote all the code there. The code is coming from our team, a complex MATLAB code. And that the very important concept in this functional analysis is the order. So some like in the when you're talking about a real number, obviously you can count the one, two, three, four. Three is bigger than two. But when you get into the complex domain or you get a vector domain, sometimes you can really compare which vector is bigger because it's in two dimensions, three dimension, 10 dimension, 11 dimension, or infinity dimensions. So if we want to compare these two vectors of infinity dimension, you cannot compare. Why? Because it takes you infinity times until universe exploded. How are you going to compare? So these are the order of partial order things, and then they have different way to define maximum. That's why I put a picture. President Xi or Trump, who is the max? It's hard to compare. And the next picture shows all the mathematic branches, all of them. And then I highlighted the one I and my students, uh, mathematical or not mathematical, whatever, we're working on. So these are our team's interest. Uh, the stuff, not all of them, obviously, it's too much. In the fractional analysis, it originally come from calculus of variations. So, for example, raising the yellow car with a red car. Okay, we want to find out which car hit the ground first. It sounds like an easy calculation, but actually no. So that's the um, original root of this course or branch fractional analysis, or where the C++ comes from. So like how this shape will looks like, and then when this soap have a area, how big gonna be area. So these are the uh, origin of the course. So we have a goal, we have an evaluation, we find a minimum, maximum. Um, it looks like um, analog to calculus. For example, we want to find a maximum. Obviously, when the derivative equals zero, you got to hit the top. Um, but when you're trying to solve the problem, we just showed before, you need to go through a number of lines. So that's exactly where the origin comes from. And that obviously because of when you working on different direction, you get into the partial differential equation or PDE. That's why I have a students used to study at the McGill PDE. And these are the equations. I won't go through it. And these are the two variables. We'll find the tips of it. Obviously, when mathemat mathematician work on it, we will look into infinity dimension, not just two dimension. Um, like when we working on the chemistry, we want to find out the soap's shape and then the surface area. So that's the equation to calculate it. So it's related to the chemistry as well. And that's the uh, Professor Volterra 1881 trying to work out this oscillation and all the nonlinear equations. So that's a fundamental things. And then he figured out when the function goes to zero, what happened? Can you find a derivative there or not? So those are the funny questions. And then you realize, oh, God, when I trying to hit the origin, it's vibrating up and down. I couldn't find it. So these are the derivative does not exist because it's a vibrating up and down. And the next more interesting things relate to our semi-theory is called a Cantor set. So now the dimensions starting to break up. So this Cantor set, uh, you have a line, but some line got to cut off. Just like our universe, the space is not everywhere. Some part gets cut off. Uh, Otherwise, the speed light won't work out. So these are called empty set. And then when you keep on doing that, you realize, crap, this line, how long is it? Zero, because you cut everything out. So that's the interesting part of a math. And that's the Votora study on how the signal goes like that. These things usually happen when there's a nonlinear effect. So when it's nonlinear effect, you will have very funny functions and have very funny derivatives. I will not go that too much detail. And when Volterra studied those kind of funny derivatives, they find out they couldn't do integration. So the next scientist called Lebesgue, a French mathematician, he figured out a new way to do the integration when it hits. The problem with those vibration up and down is called a Riemann integration and a Lebesgue integration because in the normal integration we go like that. We slice the area into a vertical. And then, but when we do that, sometimes we couldn't get integration done. So we change it. Instead of slice vertically, we slice horizontally. And then we figure out, now we can do integration. Okay, so those are the first section I want to talk. The next section, we're going to go look into the space. So previous section is really about infinity. Infinity large, infinity small, infinity close, and then couldn't do integration. Okay, let's change the direction. Because the mathematician is either work on the algebra or geometry. When we do geometry, we look into the shape. So these are the torus, we call it. Like a Microsoft doing all the encryption using this shape. So that's Microsoft encryption. And this page shows the notation we use. And that's the linear space. Linear space is you count with your fingers. Addition, multiplication, very simple. And the norm is the distance. In ancient Egypt, how high is the perimeter? It's 280 kins able. So the kins sleeping in that perimeter, 1,000 years, a few thousand years. How high is the perimeter? 280. Don't know why he picked that. Anyway, that's a high. So that's distance. And in China, uh, Chinese king, he said the guy who Tang Dynasty is most uh, prosperity dynasty uh, in China. That's why every China town is called a Tang Dynasty town. How long is Chinatown's food? That's the emperor, the feet. How wide his feet? Each feet is 1 foot. Is the distance. And then when we look at the United Kingdom, um, the king's thumb is 1 inch, where the 1 inch comes from, king's thumb. So that's we have different distance, called one, two, or infinity. As I told you, the mathematician work on nothing but the infinity. And in this uh, space, we have a lot of theory. One interest theory is called fixed point contrast mapping. Bear in mind, we look into the space with infinity dimension, not just the two dimension, one dimension. And when we play with the topological space, it's basically um, it's like a Costco membership. You're either in or out. So these are called a topology. It's about a set, whether you are in or you are out, if you have a club call or not. And these are the measuring. You're measuring the distance. And once we have those space sorted out, we can look into the operators. Operators that works on either geometry or algebra, it doesn't matter. Because the geometry algebra are related. I will show you on the last few pages. So these are called the representation theory, representation theory. It defines, first of all, we have defined orthogonal. Like when we do 5G, we have a X and a Y, sine, cosine, they are orthogonal components. And it has to be closed vector. A closed open means you are in club or you're out of club. And it's a Hilbert projection theory because sine, cosine are projection. And it has to be non-empty set and it has to be convex subset because when we do optimization, we want everything convex. And it's in the Hilbert space. And then we can find the minimal or maximum. And this theory was early used to derive Parseval theory, Fourier transform theory, Bessel inequality, blah, blah, blah. So those are the coming from the thermodynamics because the Fourier used to study physics. So those are the inner product, inner product in Hilbert space. The space that's the element is complex. It's not the real. If it's a real, we usually deal with the Euclidean space. But when elements are complex, we deal with Hilbert space. The same thing for the quantum. In a quantum world, we deal with complex element. And these are the inner product. Inner product, it's sort of like a correlation or it's like a projection from one vector to another vector or from uh, itself. It's a projection on itself. From this theory, we are able to see the frequency domain is equivalent to the time domain. Energy is conserved. So these are the FFT. After FFT, the frequency are mapped. However, the energy are same. These are the where FFT comes from, the DFT, discrete time Fourier transform. And the functional analysis are working mainly on Hilbert space or on complex. So Euclidean space mainly work on a finite dimension vector space using a real number. So that's the major difference. The Euclidean space is a finite. and then it's a real number. But the Hilbert space is infinity dimension and a complex number. That's why I say if you want to work on science or engineering, you need to study this, Hilbert. And these are the surjection relationship. Um, I did not translate this part because you can see from the picture. I do translate those word one-to-one called injection, onto called surjection, bijection. So that's the projection. And then there's another concept called a category uh, or functor and a subcategory. Uh, this functor is a function operator. So it abbreviated called a functor. So of everyone know operator, function, and a function operator is called a functor. So the functional analysis works on the functor. And then it study is this functor dense or not dense? So these are the issue um, in the logics. And the most important theory in this part is called open mapping theory. So if the E to F is a surjection, continuous linear map between this space, or more generally, fresh space. Um, when you see these Euclidean space, Hilbert space, Bonhoeffer space, uh, and even more like when we study MPPK, we're working on even generalized space. Uh, what does that mean? It means you have kind of rules there. Like you are in a club. Every club have different rule. Costco and the Sam's Club has different rule. So it depends how many rules they have. The more rule they have, the more concrete they are. Less rule they have is more abstract. Um, when we do post-quantum encryption, we need a space has less rule or more general. So these are the NT is an open mapping. So these are the open mapping theory. Why we need all those concrete rules? Because sometimes we need to solve the equation, like a Volterra integration. So this integration, the kernel is changing. This kernel is changing. So why your integration things changed? It's like why you're doing your homework. The teacher changed the questions. Well, usually student will complain, but those are called integrate. Very funny integration. You need less row space to play with. And these are the direct sum. Uh, so when you have a space M and a space N, you want to create a bigger space X. So that's called a direct sum. If you have 2 times 2, that will becomes 4. If it's 2 times 2 times 2 becomes 8. And these are the closed graph theory. Like this one is closed, this one is not closed because there's a jump. And that's the fixed point theory. Uh, this theory is trying to make sure you are able to obtain a solution. And sometimes you may say, hey, find a solution is not that hard. Wait a minute, but if your space is infinity dimension, then that's a big problem. So because we working on infinity dimension. So we need to find out whether there's solution or there's no solution. And also we need to find out it's bounded or non-bounded. or uniform bounded. So this is called a resonance theory. And that's the usage. With that, we are able to find the Fourier transform. Uh, it gonna be converge or not converge. And these are the theory for the functional uh, analysis, whether we gonna have bounded solution or unbounded solution. And then this definition of a semi-norm. Norm is the distance, so these are semi-distance. As I said, like sometimes we can't compare. Why? Because it's infinity. So we need to set up some kind of rule there. And these are the usage of those theory. And finally, I can have a quick, well, we run through one, two, three, four, five. So there are big five theories there about the operator. And then now finally we get the spectrum. So we'll look at what is spectrum. And when we look at the spectrum, the things are begin even bigger or complicated. So let T be a bounded linear operator acting on Banach space X over complex scalar field C, and I be identity operator. It's like a one or unit in the vector on X. The spectrum of T is the set of all lambda belongs to C, for which the operator T minus lambda I does not have an inverse. That is a bounded linear operator, uh, which means T equals that. So since T minus lambda is a linear operator, the inverse linear if it exists, and the bounded inverse here, it is bounded. Therefore, the spectrum consists precise of those scalar lambda for which is not a bijective. So that's a spectrum. What does that mean? That means these T can be decomposed into different directions with a scalar lambda complex. Lambda is complex. It's not just one, two, three. It's complex. So the T, you can think of a mapping. This mapping or this operator can be break down into different directions, X, Y, Z, or until infinity. This lambda can be infinity. So that's called a spectrum. That's the FFT, where the FFT will land you on. And these are the theory operators, and kind of showing you why this complex number is the spectrum. Remember when we get the brain wave, it's complex number. It got the amplitude and the phase. So that's the spectrum. And this theory is called kind of conjugate theory. So when you do conjugate, these things still hold for you. In real number, you don't have that, but in complex number, you will have those conjugate and inverse. And also you are talking about this normed vector space. Norm means distance. So you can compare the two vectors, who is longer, who's short. You We need to do that when we do like Amazon recommendation algorithms. And a spectrum is turned out is a compact. So these are the theory. Why is compact? Because it's already decomposed and it's running on orthonormal basis, and it's countable infinity. It's infinity but it's countable and it's compact, which means there's no holes in between. And these are the radius of the complex number or space when they decompose it into direct sum. So these are the direct sum, which means you can projection your operator into all different directions and then sum them up. And that these are the determinant of the matrix. Again, this matrix can be infinity. Don't expect using MATLAB to calculate it. And these are the convolution Fourier transform. So the convolution, it shows like when you do those direct sum or direct multiplication, you end up with a tensor products. That's like a TPU. And because the deep learning is just using the sort of convolution or correlation, actually correlation operation, that say this formula or theory, convolution theory says you can do it time domain. You can also do it in the frequency domain. That's why we do FFT for brainwave. To summarize all I talked today, we have to using a very uh, abstract theory called the Langlands. Langlands is a Canadian. Langlands is Canadian. He used to teach at the Princeton University. Um, my student is also his student. So Langlands basically studied this L group theory, and then he unifies geometry with algebra. He maps every algebra into geometry and then max his students maps all the geometry back to the algebra. To explain what Lenin's Canadian mathematician did, we can look at the Z transform. Everybody knows a Z transform. So this is xn z to the power of next to n. So that's why they say n times of z. That's Z transform. And then you look at another transform, which is called L function. Um, now we exchange the position. Here we sum from n from 0 to infinity, n 0 to infinity. But this is n is on the top, is on top. The L function is reversed. Instead of summing this index, the power, we actually sum up the base. We leave the power s there unchanged. Xn is still xn. The only difference, instead of sum the power, we sum the base. So that's called the function. L function. And then Lenin's figured out by doing this and by doing that, they're equivalent. So that's what I say n times of z or s times of n. You spinning infinity many circle in the sky. So this is a sky. When n is on the top, is you flying with your UAV drone, or running only one laps on the ground. So you're only running one laps on the ground. So you're not flying infinity circles. Because when you do this, you actually run in circle. You run in circle. When you're doing the base, you are not running circle in the sky. It is fixed. You're only running one lap on the ground. It's all done. So these are the called L function. And the usually when I try to test my PhD student in mathematics, my question asked them usually is what is the power of I to the I? So that's the question I usually ask them. What is power like it ends I? And then if you plot it, this one you can plot it with MATLAB. You find that that's why you're running on the sky. So it's the I. When the I is on the top, you're actually going like this. The n can go to infinity, but uh, your curve is still still in there. It's still in there. That's the imaginary number. Any number to the power of I is like this. That's where the L function are doing. So the L function. That's why we want to run one lap on the ground. So that's if you understand what this n to the power of I or I to the power I, you're the mathematician. And these are automorphic form. So it basically breaks down all the L functions into this product of uh, cross product, automorphic representation, or a tensor product. With when you're using this L function, you come up with a tensor and then you break it down. It's like you factor the prime number. And these are law of a conjecture reciprocal. So that's the root of the Langlands program. That's where these L function come from. So it actually is very kind of interesting questions that tailors usually ask. Like I do a adult, mom and dad's clothes, and I have some leftover clothes. I want to make a diaper, the squid diaper. So that's the Langlands program. Very complicated. And that's the L functor, functional operator. Uh, the When I work at the SESTEC, uh, we invite a French mathematician give a talk on this L functor. Why we studied so deep in the L functor, but it's actually related to the encryption. So these are the relationship. When we study those L functors, we were able to decompose L function into the different root, like the root called the pentagon number theory. Pentagon number theory. They will find the root are plus minus 5, plus minus 1. And that this pentagon theory explain why human has 5 fingers. And also explain why the money are 50 cents, 500 cents, 5,000, blah, blah, blah. And these are the book wrote by my student, Professor Joe. He teach in the medical school in Texas. And these are the original letter Langlands, Canadian mathematician wrote, uh, but he forgot put the data there. Trying to figure out the L function. That's what he was working on. This is a mapping uh, for the functional equation. And this mapping is the mapping we use to analyze the COVID-19 and the flu A virus genomic. Exactly this mapping we used to predict when that COVID-19 will end it. And these are the picture when you plotted this original uh, mapping related to the Albert Einstein relative theory as well. And the next slide shows another module representation is called a Lie group. Because as I said, Langlands related algebra. Lie group is algebra. Lie group is created, founder of this Lie group is Harris Chandra. Harris Chandra come up with this idea, and then he maps the geometry into the algebra or algebra into the geometry. So that he pointed out actually they're related. And Professor Ichiro, Japanese professor, he figured out manifold, three manifold theory. And then you plot it, three manifold, it looks like that. It looks like soccer ball. It basically says the algebra or uh, automorphy decomposition are same as the Lie group. And that's the summary of Langlands program. So it's in mathematics, there's only one program. It's called the Langlands program. It's very much like the Max or Communist Party's program, very similar. So this mapping shows every geometry by using modular, you will end up automorphism. Automorphism means you maps to yourself. Like a galaxy is big, but when sun look at it, it's a small. Because when Earth running around the sun running around the galaxy, when you live 100 years old, you're running around sun for 100 circles. Same thing for the sun. When sun running around the galaxy 100 circles, sun is dead as well. So that's called automorphism. When you Earth look at the sun, just like the sun looks at the galaxy, the same thing. So that's called automorphism. So you just study one and you know everything, small or big. And the Galois is the algebra. So these are algebra. The, the relation between algebra, geometry is through this conjecture, Fontaine-Mosé conjecture. Lalanne's basically standing here, automorphism. So that's why my theory is a fractal. I'm standing at the same place. That's where the symmetry. And that's also the application. Like currently, the bank are using elliptical curve encryption. So that's the elliptical curve used today by the bank. But now we're gonna upgrade it, maybe using MPPK, uh, PQC. We're gonna using quantum version because the elliptical is the two-dimensional. We're gonna using three-dimensional or infinity dimensional post-quantum encryption to help the bank fighting with the hacker. And that's from algebra representation. And it's fully descri descriptible by the L function, which I explained. In the last slides, I'll also mention that this theory is also related to quantum field theory, Langlands program. Uh, the connection is through a complex number defined by this formula. Uh, that's for the coupling constant used in the Young-Meal theory. Uh, Professor Young just passed away. I think it last month or recently. um, the great physicists who solved these quantum equations. Okay, that's all. And the last page is my this is my Chinese phone number, and that's my Chinese email number, and those are the all my social media pages. Thank you.